Now let's add the second identification. The identification of the set of the compatible collections in this object.
Let's first define the map from left to right. Let psi be a natural transformation from G to pi star f. We would like to find the compatible collection on the right hand side. As usual, we'll take some open subsets. V prime V, U prime U. Pi of U prime is always required to be contained in V prime, and pi of U is contained in V. We wish to complete this diagram by finding the vertical maps such that the square we get will be commutative. To this end, we need the help of psi and pi star f. For our lower part, we simply recall the definition for the pi star f. Since pi of u prime is contained in v prime and pi of u is contained in v, this pi inverse of v is larger than u, and pi inverse of v prime is larger than u prime. So we get the restriction maps in here. Since both squares are commutative, this rectangle is commutative. Now we define the map gamma from this guy to this guy by sending psi to the collection of the composition of these two arrows. And by the commutativity of this rectangle, this is a compatible collection of maps. So this gamma is well defined. Okay, now let's construct the map along the opposite direction. Let psi sub VUs to be a compatible collection. What we need are maps from G of V to pi star f of V for all V's. If V prime is contained in V, we look at the definition for pi star f. We see pi inverse of V can play the role of U, and pi inverse of V prime can play the role for prime. And pi of pi inverse of V is contained in V, and pi of pi inverse of V prime will be contained in V prime. So pi of pi inverse V is contained in V, and pi of pi inverse V prime is contained in V prime. So the conditions for the compatibility are satisfied. Now by the definition of the compatibility, we have maps psi sub V pi inverse V and psi sub V prime pi inverse of V prime, and it commutes with the restriction maps. So we will simply define our natural transformation from G to pi star of f to be psi sub V pi inverse of V, and psi will be a natural transformation by this commutative diagram. For this map, which we denoted delta, will be the map sending psi sub VU to psi we get from here. Psi sub V is psi sub V pi inverse of V from this compatible collection. And now we need to verify that this delta is really an inverse to gamma we defined above. To this end, we first take a psi, a natural transformation from G to pi star F, and we check that delta composed with gamma acting on psi will give us psi itself. By definition, gamma of psi is equal to the compatible collection consisting of the restrictions composed with psi sub V. So this is equal to delta of the collection restriction composed with psi sub V. Now, what is delta acting on this collection? By our definition, for delta, we want to replace this U by pi inverse of V. But this gives us an identity. This is identity. So we get a collection of psi sub V's. This can be immediately identified with psi, because psi itself can be regarded as a collection of psi sub V's when V ranges over all open subsets of Y. On the other hand, gamma composed with delta acting on an arbitrary compatible collection will be equal to some gamma of psi, where this psi is defined in this way. And this is equal to the collection with individual terms to be the composition Now we plug in this equation into here, and we get the restriction map composed with the map in the compatible collection. From here, we can immediately recall the definition for the compatible collection. There's a commutative diagram saying that the restriction composed with a map in the compatible collection will be the same as another map in the compatible collection composed with a restriction. Specifically, this composition is this composition. Since this diagram is commutative, it will be equal to this composition, which is psi VU composed with restriction VV, and this is identity. So we get what we started with. So delta is really an inverse to gamma, and we have established a bijection between them. So far, we have established the bijection between the set of sheaf morphisms from pi inverse G to F and the set of sheaf morphisms from G to pi star F. But we haven't checked the naturality, and now we will do this. There are two commutative diagrams that we need to verify, but here we will only do one of them. Let M from G to G prime to be a sheaf map. a natural transformation between functors. We want to verify that these 4 objects gives us a commutative diagram. Of course, we need the help of this object and those 4 maps. Actually, here we need alpha and delta. We add objects and arrows in the middle. And let's check this square and this square are commutative. As a result, this whole rectangle will be commutative. Let's first look at the square 1. We take a sheaf map in here. Call it phi. M star composed with alpha prime, which is this composition. We apply it to phi and use the definition for alpha prime, and we will get M star of a compatible collection defined by taking the composition of 3 maps in here. This is the composition of 3 maps. For simplicity, let's just write psi sub vu from G prime V to F of U. And the M star of this is the composition on the right. Okay, so let's leave this alone for the moment and look at the other composition. This part will be the composition on the right, and alpha of this guy will be the collection, will be a compatible collection, and this is also a composition of 3 maps in the definition. And now we want to check that this guy is equal to this guy for every pair UV. And now let's prove this. The proof of this claim is given by tracing the following diagram. The right-hand side of this equation is equal to the composition of those 3 maps. And the first part is exactly this guy composed with this guy. But using the commutativity of those 3 regions, we know the composition of those 4 arrows will be equal to this guy composed with this, composed with this, and this. And you may wonder why this triangle or this region is commutative. It is commutative because recall the definition of phi sub vu. So this phi sub vu is a composition of 3 maps, and precisely those 3 maps. So this region is commutative because of the definition of phi sub vu. So by the diagram tracing, we finally will get M sub v composed with phi sub vu. And we are done. This is what we want to prove. Okay, now let's prove the commutativity of this second part a second square. In the proof of this second part, we'll take a compatible collection of maps in here. We first apply those two maps to this compatible collection. And M star of this guy will be the composition on the right. What is delta of this collection of compatible maps? Here's the definition for delta. It will send a compatible collection of maps to a sheaf map from G to a push forward. And this psi is defined by letting the open subset U in X to be pi inverse of V. Let's forget about the details in this definition. For the moment, let's just denote this guy psi tilde. And now let's apply those two maps to this collection. This delta prime of psi sub Vu will give us a sheaf map psi. And this is equal to psi composed with M on the right. To prove that they are the same thing, we will apply both of them to open subset V. By definition of delta and delta prime, psi tilde sub V will be equal to psi sub V U, and this U will be replaced by pi inverse V, which is the definition of delta. Also, it should be composed with M sub V, because we are considering this thing as a whole. And this guy, what is this guy after applying to V? After applying to V, it will be psi sub V pi inverse V composed with MV. Same thing. So we have proved the commutativity of the second part. So both 1 and 2 are commutative. So this rectangle is commutative. Of course, in the definition for the adjoint pair, it's another commutativity diagram we need to check, associated to beta and delta. But the proof, I think, will be similar, so I will skip the proof of that part. So we have proved pi inverse and pi star form an adjoint pair.